Hi everyone. So this here is an optics problem. It says that we have someone who's 2.2 meters away from a mirror. The mirror is 83 centimeters off the ground, and the man is 1.72 meters tall. And we're asked right here, we have this distance that we can't see, right? The man will see, when he looks in the mirror, he's only going to see here, but not in this space here. And we're just asked to quantify how much of that space to the mirror there is, right? How much of the floor is he not seeing? And this one's a pretty easy problem. You just have to be good with the math and the trigonometry. And it comes down to one finding, and I think that you'll see it pretty simply. Let's divide these visions into triangles. That's what I like to do typically. So notice that there's a triangle here with his eyesight to the edge of the mirror. That we also have the mirror length, the height of it, and then we also have this imaginary space here, which is defined to be 2.20 meters. Okay, so when you see this, I think for some of you it might be like, aha, I see what I have to do. But if not, let's go through it. So my thought process is that, and I'm going to use green here to signify this, I have some angle theta here. Okay, theta just means an angle, and I know that there's an angle here. Well, then I also know, because of the law of reflection, right, the incident angle equals the reflected angle, right? I know that this angle, with this imaginary little axis here, with the parallel with the mirror, I know that this angle must be true. And notice I know that the side length here is 38 centimeters. I can use some sort of trig identity to find x. And if you don't see it, let me just walk you through it. Okay? And let's actually name these. This is going to be the incident angle. This is going to be the reflected angle. Okay, so let's define theta I. Okay, and that's going to be this angle or this length that we don't know. In this case, it actually won't be that important. So I'm just not going to even draw it. We have this side length that I do want to know. Okay, and I also know that this is 2.20 meters. Okay, so there's some angle, or there's some length here that I need to find. And I can do that. I notice that this is 1 meter and 72, and then this is 38 centimeters. If I just do some simple math, let me grab a calculator here. If I do some simple math, I can find 172 minus, and if this was converted into meters, it would be 0.38 meters. I would find that this length here, right, of the mirror itself is 1.34 meters. That means that this side length is also 1.34 meters. Okay, so hopefully you can see that there's an identity here, and it's going to be the tangent identity. Okay, tangent of theta of the incident angle is going to equal the adjacent side of 2.20 meters over 1.34 meters, and this will give us an angle theta. Okay, so let's just solve it. We're going to take the inverse tangent. You can call it tan to the -1. I like to do it arctan because it's not really tan to the -1, right? Because that would be 1 over tan, which is cotangent, and you do not get that. And just a little rant. I love math rants, but I also hate them because they take your time up. So the incident angle I is equal to arctan of 2.20 over 1.34. And when we do that, let's see what we get. Okay, so inverse tangent of 2.20 over 1.34, that's going to give us an incident angle, in this case of 1.02 radians. So let's just convert that, and that's in pi radians, so I have to do a little bit of math. If you want to convert to pi radians, you multiply by 180 over pi, and that will give you the angle in degrees. Okay, so theta I, if I could put it in my I had too much coffee today, and my brain is all over the place, to say the least. Okay, so theta I, or the incident angle, is 58.4 degrees. All right, so I'm not worrying about sig figs right now. I'm going to keep maybe 1 or 2. Let's see, we have 2 sig figs, right, because that's given in 38 centimeters, not 38.0. So incident angle, we now know is, if I could write, 58.4 degrees. Okay, so now we're going to erase all this work and find now this angle here, and then we're going to find delta x. Okay, so if you remember the law of reflection, let's say that you have a straight line here, a light ray comes in at this angle, let's say some theta, right? Well, the reflected angle is literally going to be equal in magnitude. So let's call this angle now phi. So phi is just kind of theta, but you flip that line going through it. So then the law of reflection would say that these two are equal. Okay, theta equals phi in this case, right? So incident angle equals the reflected angle. Okay. I'm pretty sure most of you know that. It's not a really hard law to understand, right? But anywho, let's get back to it. Now let's draw our other triangle. Okay, now I'm just going to make the jump here. I know 58.4 is the incident angle coming into the mirror. I know the reflected angle here needs to also be 58.4 degrees. All right, I know the side length is 38 centimeters, so what is x, right? That's what we want to know. Well, what we're going to do is we're going to just do another tangent identity, right? We're allowed to do that. No, notice it's not going to be sine or cosine because the tangent is not defined here. It's only a side length. So let's say tangent of 1.02, right? I'm going to stick it in radians just because that's my calculator. That's what it's saying. Is the adjacent side over 38 centimeters. Okay? So all it's going to be is 38 times tangent of 1.02, and we'll get our answer in centimeters. Okay, so x here, when you do the math, you multiply this over, you get 61.9, and we have two sig figs, so 62 centimeters. That's going to be your answer for this problem. Sorry, I got a little cut off there. I have my laptop here charging, so the thing I'm recording on. But that's all there is to it. Pretty simple problem. It's just kind of tedious math. It's 62 centimeters. And the two things to take away here is remember your trigonometry, right? That's very important. But also incident angle equals reflected angle when you have a plane mirror, although it does change when you have a concave or a convex mirror. As we'll see in a future problem. So hopefully you guys enjoyed this. If you did, please drop a like, comment, and subscribe. I would greatly appreciate it. And I hope that you have a wonderful day. Bye-bye.